All right, guys. Mr. Gucci here with the second part of your notes. Maybe? You gonna load? Is this loading? It's loading. All right, cool. So, we're going to talk about some of these different particular units that I introduced in the last section. The first one we're going to talk about is temperature. All right, now, what is temperature? You might be like, oh, it's how hot or cold something is. Yeah, sure, but what temperature really is? It's a measurement of the average kinetic energy, meaning the average vibration or movement of particles. The hotter something is, the faster it is moving. The colder something is, the slower its particles are vibrating. Even things that don't look like they're moving, like, this pen, right? It has a certain temperature, room temperature, so I don't know, what does my house say? 72 degrees Fahrenheit, aka about like 30 Celsius or something? Like, that is a measurement of how fast the particles in this Sharpie are vibrating. The faster you vibrate, the higher your temperature. When you heat something up, you are just putting energy into it so that its particles vibrate faster. When you are cooling something down, you are absorbing that vibrational energy. You're dampening it so that the particles bounce around slower. Now, this, by the way, this is why stuff cooks. All right, if you get something hot enough, if you get its particles vibrating enough, it will actually vibrate so hard that its molecules will start to change shape or even break apart. And that's what causes meat to go from not cooked to cooked. You vibrated it so much that its particles start to shift and its molecules break down, right? That is the cooking process. That's also why you happen to get a fever when you get sick. You see, when your temperature goes up, you're just vibrating your body's particles faster. And if you vibrate them enough, you can actually cause the molecules that make up viruses and bacteria to break apart and break down. That's how our body fights things that we can't even see. It just vibrates your body so much that it destroys them. Now, the danger there is if you vibrate your body too much, if you get too hot, all right, you'll start to break down your own cells, your own molecules, which is why if you have a prolonged fever over 107 degrees, if you have that long enough, you will actually get permanent brain damage. You will cook your brain. You will vibrate the molecules in your brain so much that they will start to change shape and undergo chemical reactions. So if you have a really high fever, they'll give you medicine to reduce your fever, but like in the immediate term, they're going to throw you in a bucket of ice water to chill you down. That's how they saved your life from having you cook yourself to death. Okay? Now, again, the metric unit was all about making measurements simpler. All right? So they said Fahrenheit, that's dumb. Why is something 0? Where'd that come from? Why is something 100? Where'd that come from? Honestly, all right, it was real dumb. It was like, for Fahrenheit, it was like, oh, it's really cold outside, so that'll be 0. And we're like, no, it's really hot. It's about as hot as it ever gets. That'll be 100. So basically, it's like the coldest it gets outside is 0. The hottest it gets outside is like 100. Well, those are Europeans in Europe. If they lived in Arizona, things would be a little bit different. I don't know. I wasn't back there then, okay? So they wanted to come up with a better system for measuring temperature. They came up with the Celsius scale. Now, the Celsius is like a bit more official. They said, okay, let's take the freezing temperature of water and call that 0. Because the freezing temperature of the water is basically the same wherever you go on Earth, basically. And then let's take the boiling temperature of water and call that 100, okay? Let's take the temperature where water slows down until it gets a solid and call that 0. Let's take the temperature where we vibrate water so much that it turns into a gas, call that 100, then chop it up into a bit. All right. By the way, the other term for Celsius is the centigrade scale. Centi, meaning, like we talked about before, that prefix means chopped up into 100. All right. That's why you have dollars and cents. All right. Cents are 1/100th of a dollar. Okay. So that was the Celsius scale. But even still, like, they could have done better. All right. First of all, why the freezing temperature of water? What makes water so special? All right. Also, you can have a negative Celsius. All right. So, like, why are we starting this temperature scale where, like, 0 isn't really 0? You can get colder than 0. All right. And we just take for granted that, like, you could have a negative temperature. Like, why does that make sense? You can't have like a negative like weight or a negative volume. You can't have a negative length. Why are we allowing a negative temperature? So then they devised something called the Kelvin scale. The Kelvin scale is just the Celsius scale, but they shifted it over so that now 0 is real 0. And you're like, real zero temperature? What are you talking about? If temperature is just the measure of how fast particles are vibrating, well, then there's only so much you can slow down those vibrations. Eventually, you can get those vibrations so slow that they stop. And there's nothing slower than not moving at all. And we call that absolute zero. There is a temperature that is as cold as you can get. All right? Where all particle movement stops altogether. Nothing moves, nothing vibrates. It's purely theoretical, and weird things start to happen, like liquid helium turns into a solid, and like things start, electricity doesn't slow down inside of objects, and it can just go in a loop forever. Look, nothing. Nothing is at absolute zero. Even the deepest, darkest regions of space are still like 1 or 2 Kelvin. All right. Why? Because there's like a little bit of starlight from like billions of miles away, just like pew, pew, pew. That little bit of starlight is enough to heat it up by like 1 or 2 Kelvin. Even in labs on Earth, we've only gotten contained areas down to like 0.00000001 Kelvin. It's like, what about the why? It's like, well, when you try and look in and measure it, like a little bit of light energy gets in. You just can't get all that energy out. So it's kind of weird to think that the coldest place in the known universe is in a lab on Earth, because we've gotten it colder than deep space. All right. Absolute zero is super freaking cold. All right. It's negative 273 Celsius, which is like negative 480 Fahrenheit. I forget. I don't know. I don't know Fahrenheit that well. All right. So, like, listen. So if you're like in a science fiction movie and they say like, "Oh my God, it's gotten down to like negative 4,000 Fahrenheit," well, clearly that was written by an English major, because you can't get that cold. All right. There's a limit. You can't get any colder than negative 273 Celsius, which is 0 Kelvin. Okay? You can't have a negative Kelvin. This also makes calculations a little bit easier. Okay? So here, by the way, is the calculations we're talking about. Okay? To convert from Celsius into Kelvin, you just add 273 to the Kelvin temperature. Okay? You just add 273 to it, and you get the Kelvin temperature. So, for example, deep space is a temperature of negative 270 Celsius. What is it in Kelvin? Well, let me show you. Okay? Kelvin equals Celsius plus 273. So the Kelvin temperature is going to equal negative 270 plus 273. The Kelvin temperature is going to equal 3 Kelvin. All right. The symbol for Kelvin is just K. No little degree circle. All right. None of that nonsense. We're not having degrees K. It's just K. All right. We got to make sure we have that unit on there. Okay. Let's try another one. Okay. Bam. All right. Convert negative 37 Celsius into Kelvin. Okay, Mr. Gucci. Let's do it. All right. So again, the Kelvin temperature is equal to the Celsius temperature plus 273. So the Kelvin equals negative 37. Is that what I said? Yeah. Negative 37 plus 273. I am not going to write meter throughout this entire year, so I just apologize and tell you to, deal with it. Sorry, not sorry. Negative 37 plus 273. That temperature, negative 37 Celsius, is 236 Kelvin. 236 K. Okay, let's do one more, little tricky one, right? A teacher always want to end on a tricky note. How about this? You go vacationing in Canada. You go vacationing in Canada, and the did I make a mistake clicking that? And the temperature outside is 300 Kelvin. 300 Kelvin. Now, what is that in Celsius? Well, now that I just opened this up, let me quit it out again. Boink. All right. So check this out. In this case, I'm giving you, all right, algebra time. I gave you the Kelvin temperature, which was 300 Kelvin. And that's equal to the Celsius temperature plus 273. So we're trying to solve for Celsius, which means we're trying to get it by itself. So we subtract 273 from both sides. Cancels out over here. And on this side, 300 minus 273 is 27. So the temperature equals 27 degrees Celsius. And that's how you convert between the two temperatures. It is like basic, all right? So I hope you were like, if you didn't enjoy that, you're at least like, well, at least it wasn't hard. That's all I can do, guys. Have a great